Subscribe now and press the bell icon. Never miss an update.
Constant time synchronous binary counter with minimal clock period. So in this we are designing a binary counter such that it is synchronous with the clock, and the minimal clock period means it is limited by the LSB of the counting rate. So here we are trying to design a binary counter in such a way it produces the constant time, means constant delay for n is equal to 8 to 128 bits. So when compared with the existing methods, what is the disadvantage in the various synchronous binary counters means the propagation delay is increased as the end operation of the inputs and outputs to the number of flip-flops increases, the link increases. As that link increases, that conventional binary counter delay is affected. So we have gone for the implementation of synchronous binary counter based on backward carry propagation. So what is this backward carry propagation? Is for every individual flip-flop chain of AND gates are being implemented, and for the output is directly given as input to the next flip-flop. In such a way, individual gate links are provided for each flip-flop in such a way that backward carry propagation is given, and the overall delay of the 8-bit synchronous counter when compared to the conventional is reduced. So in such a way we are trying to improvise the performance of the counter design. But the major disadvantage in the synchronous counters is, one of the disadvantage is the fan out. So the fan out issue is because of the control signal which is given as common to all the flip-flops. So as the number of flip-flops increases, as the bit width increases in the binary counting, that counter data rate is seriously affected as the maximum fan out is gained, and in this affects the data rate of the counting. So in order to reduce that, in order to optimize the maximum fan out issue and to optimize the delay issue, we are going for a pre-scaled implementation of counter. So in this pre-scaled means it is previously like segmented, the counter which we have to implement, that is segmented into parts, and after that the counting operation is performed. That's why it is called as pre-scaled counter. And to perform that counting operation and to reduce the fan out, we are going for the different enable inputs enable inputs by generating through ring counters. So in such a way we are trying to reduce the fan out of the counter counter CNT signal. Although if we tried with that pre-scaled enable also, the last n-bit counter, which is 58-bit counter, consumes the signal for 53 flip-flops, so it doesn't affect much when compared with the conventional. So we are going for one more design which is n-bit counter, which is segmented into 3 different sub-counters. So in these 3 different sub-counters we are trying to utilize a Johnson bit counter which is constructed for 1 bit, and by multiplying it by utilizing it multiple times, we are generating different signals for the different blocks, and thereby we are trying to optimize the fan out, and we are trying to achieve the constant delay for a particular bit width from n is equal to 8 to 128 bits. So in the C1 counter, whatever the CNT signal is there, it is propagated to a 1-bit counter as well as 1-bit Johnson counter. So here the Q0 output is generated from the C1, as well as the second enable signal to the C2 is generated, which is pen1. So this based on this pen1 for n minus bit backward carry propagation, which we have seen in the figure 2 implementation, that is implemented, and n-1:1 outputs are generated, and based on the end operation of these signals, which are acting as enable signals to the 1-bit Johnson counters, which are multiple times duplicated to generate the pen2 signals, which are the third enable signal to the third block. So based on this number of enable signals, this conventional binary counter with bit width of capital N minus small n is segmented, and maximum fan out is restricted to a particular value by segmenting them into a particular number of signals, and based on that we are trying to optimize the fan out. Here we have considered that maximum fan out of that particular Johnson counter is restricted to 16. So now how that m signals are generated? So based on the seal value of that capital N minus small n by L, we are trying to generate small m signals. Now what is this capital N, what is this small n, what is this L? So L is the number of input ports that can be driven by flip-flop, which is in short fan out. So small n value comes from the maximum of by taking the log operation, ceil of log operation of capital N. So capital N is the number of bit width. So for example, if we are considering, we have considered a range of 8 to 128. So for example, we are implementing for 64 bit, then capital N is equal to 64, and then small n becomes log to 64, and small m value is n minus n by L. So in such a way we are generating small m signals for capital N minus small n bit conventional binary counter, and thereby the remaining bits are generated. So in such a way we are trying to design a counter by segmenting it into different blocks, and we are generating different signals for different blocks, and thereby optimizing the maximum fan out such that it can produce the same fan out, that is 16, and we are trying to achieve a constant delay for any bit width counting. So in this way we are trying to generate a binary counter with constant time by restricting the clock period at the data rate of initial LSB, which is Q0. So in such a way we are designing a binary counter, and these can be implemented in various implementations like analog to digital converters, frequency dividers, PLLs, synthesizers, etc.